So at this point, you've probably realized that for every single function that we've done, we've used this definition that let P of x and Q of x be polynomials with no common factors other than one, right? And this is our general rational function. But today we're going to talk about something that we call holes or removable discontinuities, which only occurs when there are common factors between Q and X. So what happens if we have a common factor, Ms. Masood? That is when a hole comes in. All right, so let's just go over some ground rules, and I'm more going to show you than tell you what it is. So a hole is also called a removable discontinuity, which means that it is non-existent on the graph. It is exactly what you think of. It is a hole. So like if I have a graph, it's going to look something like that. And just like in any function and any number line that we've done, right? If I have like x is greater than 2, I go to 2, right? 0, 1, 2, and I put an open circle to communicate what? What does that open circle communicate? It communicates that all values leading up to 2 exist, but the actual value at 2 does not exist. So if I have a function like this, right? So x is x is greater than 2 and x is less than 2, so that everything exists except for what the value is at 2. So the open circle communicates that the value at that point does not exist. Removable discontinuities only exist if P and Q have a common factor. Remember, the domain is applicable to the original function, right? So for functions that we've done in the past, we've always said, like when we were doing them in the very beginning, when you were doing things just like simplifying, I told you first find your domain, then cancel common factors. And you're going to see why I emphasize that in the beginning, because for a problem like this one, let's move this down a little bit. So for a problem like this one, and we're going to find all the different parts of this problem, but what we are first always going to do is find your domain. So I already factored it beforehand just because to save some time in the video. So the domain is when the denominator cannot equal 0. So it's going to be all real numbers, but x cannot equal -2 and 1. Right? So I'm going to write that here. All real numbers, but x cannot equal -2 and +1. Okay? That's really important here. Now, if let's say this didn't exist, right, and there are no common factors, we would automatically jump in and say, okay, my vertical asymptotes, that means are x equals -2 and x equals 1. My horizontal asymptote, we can make we can find that out. But there'd be no holes, and my x-intercept would be -1 because you just set your numerator equal to 0. Here's the problem now. Because I have this discontinuity, right? I have this common factor that I can cancel out. Technically speaking here, this is really equal to x. Let me put this in a different color. This is really, really equal to, and I'll do it like this. I cancel these out. This is really equal to x plus 1 over x minus 1. But does the domain stay the same? Yes. So the domain does not change. So that means, what the heck happens at x equals -2? Well, it doesn't exist because it's not part of my domain, but technically, I am graphing this right here. I am not graphing this. I am graphing this function. Everything else right here, I'm going to find from this function, except my domain and technically my holes. Because what happens at x equals -2 is there is a hole. So there's a hole at x equals -2. We're going to find what it is, but that's important here. So now here we have a hole because it was removed. It was a removable discontinuity. There's a hole at x equals -2. Now, in order to find what the actual point is, where is the hole, I'm going to plug it into the graph we are functioning. Oh my God. The function we are graphing. So I'm going to plug it in. So f of -2 equals, and I'm going to plug it into this function, -2 plus 1 and -2 minus 1. -2 plus 1 is -1 over -3, -2 minus 1, and so I get 1/3. So my hole is going to be, so I'm going to write it here big, so I'll write it over there too. Hole is at -2 and 1/3. So there is a hole at -2 and there is a what at -1? There is a vertical asymptote. That's why in all those videos, I emphasized for days that when you have common factors, right? We've been using this definition, no common factors, because when we had no common factors, the values in our domain went straight to our vertical asymptotes. But now that we have a hole, yes, we have x equals 1 is my vertical asymptote, which is this, but -2 1/3 is my hole because it's a removable discontinuity. Let's look at what that looks like on a graph. So here is my function. Oh, wait. Oh, wrong function. This function right here. Here's my function, right? So for this function, technically, what we are going to graph is this, x plus 1 and x minus 1. So if I look at this, if I click on x plus 1, x minus 1, notice they're the exact same graph. This and this are the exact same thing. The same way that 1/3 is the same thing as 2/6, right? One is just simplified. Now, the difference here is that for this function, all values exist, right? All the values exist. But for this function, at -2, look what happens when we reach -2. At -2, there is a hole. It is undefined. That is the key here, ladies and gents, that at -2, there is a hole. It is undefined. Everything else of the graph has to do with this function. So my vertical asymptote is at x equals 1. My x-intercept, let's look. So now I can find everything else. My horizontal asymptote is going to be, it's x over x. It has the same degree, so therefore it is going to be y equals leading coefficient over leading coefficient, 1/1, which is 1. My x-intercepts, I'm going to set my numerator equal to 0. So x plus 1 equals 0. So x equals -1. So I have -1, 0 is my x-intercept. And my y-intercept, I just plug in 0 and I get 1/-1. And that's going to be -1. So 0, -1. So let's look at the graph. Y-intercept, -1. X-intercept, -1. My asymptote is at -1. My horizontal asymptote, +1. My horizontal asymptote, what do we say it was? Y equals 1. Look at that. Let's change this up. Boom, boom. There's our horizontal asymptote. So all the other parts of my function are going to be based on the part of it that has no common factors. So all of it still stands the same. The only difference is that whatever my domain is, so if I have a domain where it's all real, this is separate. It's like all real numbers, but x cannot equal 1, 2, 3, 4, and 5. All of these x values are going to be split up to be either holes or vertical asymptotes. depending on if any of them get canceled out of the function. So let's look at another example. Okay. So I did not factor this one, so let's factor it first. So the first thing we're going to do in the numerators, we're going to take a GCF of 2 out. So we have 2 and then x minus 3 over x plus 3, x minus 3. Okay, so first thing I'm going to do is find the domain. My domain is all real numbers, but x cannot equal 3 and x cannot equal negative 3. So I know that both of these are going to be either a vertical asymptote or a hole. Okay, an asymptote or a hole. So what cancels out here? The x equals negative 3. So that means that, again, it's what you solve for. So that means that x equals 3 immediately I know is a hole because it canceled out. And that means because of that, so I could just rewrite this as 2 over x plus 3. This is where I'm going to get all my other information from. So I know that x equals negative 3 because of this. If I were to solve it, this is going to be my vertical asymptote. Okay, now the question is, just for review's sake, let's do, what is my x-intercept? Well, can I set 2 equal to 0? No, so there are none. What is my y-intercept? So I plug 0 in, I get 2 over 3. So I get 0 2/3. What is my horizontal asymptote? Well, the degree of the denominator is greater than the degree of the numerator. So the denominator is growing at a faster rate than the denominator. So it's going to be y equals 0. And we already know my vertical asymptote, and we know the hole, and we know the domain. So that's all the information that we need. So let's look at the graph of it. So again, notice how this is a simplified function. They're the same. But let's look at the actual graph. So my vertical asymptote is at x equals negative 3. We said that we had a horizontal asymptote at y equals 0. So I'll show so we can visually see that. But then we have a hole at what value? Well, let's actually, before we do that, let's figure out what the actual point is. So in order to find the point, we need to plug into simplified function. And the reason we want to plug it into the simplified function is because, well, first of all, it's going to be undefined in the original function because it gives me a 0 in the numerator and the denominator. But the reason we want to plug it into the simplified function is basically we want to know when we plug in, what is it? 3, when we plug in 3, where's the function? Where is it? So we just want to find the y value when given the x. So I'm going to plug in f of 3, and so I'm going to do 2 over 3 plus 3, which is 2 over 6, which is equal to 1/3. So the hole is at 3 1/3, which I'm sure we will see, but it is at 3 1 2 3 1/3. You can't even see it. It's technically non-existent. That's why it says undefined. But if we look at the y value. I can't point at it because I'm here, but look at the y value where it says 0.364. It is infinitely going to approach 0.3333333. But once it gets there, it's undefined, and then look how it slowly goes away from 0.33333. So it infinitely approaches it. So here's your summary. The values that are not in the domain are not invited to the party. Those not invited to the party are asymptotes and holes. I'm gonna just let that sink in. Thank you for attending my TED Talk.